So I would like to introduce the benefits of using variable resolution unstructured grid for atmospheric simulation. And I hope some of you have some experience of using the WRF model, WRF, which means weather research and forecasting model. And if you haven't yet, we might come. I will introduce from the very beginning. So there are two types of numerical weather prediction model. One is the regional model, and versus the second one, global model. WRF is a regional model. As you see, you just care about a region on the Earth's surface. So the simulation only is carried out only for the domain you define. So the domain for WRF model is restricted to be rectangular. It is because WRF require you use a map projection like the one I put at the center of the slide. And usually for mid-latitude, the map projection is something like you put a cone to the space cutting the Earth. And then there are two parallels, the two red circles on the Earth. And then you just cut out the middle part. And then you unflip that cone sheet paper out to a flat Cartesian coordinate system. Then the region in the regional model is kind of transformed. Sometimes the projection will be plotted in the way shown on the map that the top region is kind of squeezed and the lower region is kind of stretched, something like that. So there is a process of map projection when you use WRF. Nevertheless, when you use a regional model, one problem is that the period in which the forecast is valid is usually limited. For example, usually WRF model is valid for a forecast up to 72 hours only. Why is there such a limitation? You can consider this situation. Since the regional models simulate only finite domain, there is lateral boundary in this domain like this thick square denoted in this figure. Outside, you actually need a driving global model to provide what we say the boundary condition of the lateral boundary condition of this regional model. Like if some wind is blowing from the north, then the boundary condition will need some data to represent the wind blowing from the north into the region this regional simulation is simulating, and also for other lateral boundaries. So there is a dependency on an outer driving model. And however, usually the outer driving model is not fully compatible with your regional model. Say the global driving model actually needs to take care of large-scale atmospheric phenomena. And the resolution of the driving global model is usually coarser than your regional model. And also in its choice of its physics parameterization schemes, the choices may favor some schemes that are good at parameterizing long length scale physical phenomena. So it has its own solution of the atmospheric state. We call it solution A. And for your regional model, like WRF, usually you have higher resolution inside. So the choice of the physics parameterization schemes is usually a set that that will do something good for final resolution. So it can be a different set of physics parameterization schemes from the global driving model. So what's this domain? What's this limited area model? Usually regional model can also be called a limited area model. Will arrive is another solution. We will call it solution B. So there is actually something incompatible fitting from solution A to your original model that tries to reach solution B. So as the time integration, by the meaning of time integration, I mean the simulation. For example, if you want to simulate 5 days ahead, you need to run the simulation for 5 days plus a spin-up period I will mention later on. And we say that we are doing a time integration of 5.5 days. So as the time integration evolve, actually your original model want to arrive solution B, while the data fed by the global model is feeding you data corresponding to solution A. So it is actually incompatible, and as the time evolve longer and longer, something bad will happen, and the solution will be kind of polluted or spurious. And therefore, usually when you use a regional model, you just use the simulated results up to about 72 hours. And there is actually a numerical technique that try to minimize the error due to fitting an incompatible solution into the regional model. It is called a sponge layer here, but we don't need to go into detail for it. And usually a regional model like WRF can be used in a nested way. So as you see at the center, you have the cost mesh, which has a bigger area. And for the region of interest, for example, you are running weather prediction specifically for a province or a city. Then around the province or city, you can add a nested domain with a final match. Usually the naming of the domain is the outer one. You call it this domain number 1, DO1. And then the nested domain DO2 and etc. DO3, etc. So this may be some regional model that many modelers is familiar to. And then we would like to introduce the CPAS model. It has the virtue that it is a single global model, yet with refinement region and smooth transition of resolution like this example. So it doesn't have the lateral boundary problem. When solving the time integration, numerically, usually we say that the regional model is a problem with lateral boundary condition. But for this global model, there is no lateral boundary. The time integration is said to be an initial condition problem. The nature of these two problems are quite different. And then for parameterization schemes, now the mesh has some area that use coarse resolution and some area that use fine resolution. This adds a challenge to the physics parameterization schemes because the same scheme need to take care of a range of resolution. We call it scale-aware requirements for the physics parameterization scheme. But the whole model is using one parameterization scheme for one aspect. I will show you later. And each parameterization scheme should be scale-aware. At the present development of models, this is not perfect yet, and the whole scientific community is improving in formulating scale-aware physics parameterization schemes. When we go ahead, we will do something hands-on, and you just check the results and analyze. And since this is a single global model, we can have a longer period with weighted forecast. For example, you can forecast 5 days, 7 days, or 9 days. But for you to perform the computational experiments, usually we start small. Maybe we start from doing experiments for 5 days ahead forecast first. So this is the comparison of a global model and a regional model. We go to the next slide. Now we talk about domain nesting. I will say that there is inflexibility in domain nesting. This figure is from the user guide or the documentation of WRF. When you add a nested domain to a coarser resolution domain, like this one, the outer domain has a resolution of 27 kilometers. And then one nested domain, the red one, the DO2, has 3 times finer resolution, 9 km. And then also go inner, the blue one, D03 has a 3 km resolution. In constructing nested domains, there are rules. So in this figure, figure A, if one nested domain is completely inside its outer one, it is okay. And for B, if 2 nested domain is in a common outer lower resolution domain, it is also okay. However, for C, if the 2 rectangular domain overlaps, it is not okay. You cannot have this configuration when you use WRF. And also some scenario like you need the higher resolution domain number 4 to be overlapping with domain 2 and 3. This is also not okay. And also you will note that after the map projection, the rectangular domain needs to be aligned with the north to south direction, or also the west to east direction. You cannot rotate the rectangular domain according to what you want. So I take this example, look at the figure at in the right-hand side. Say I want to do a weather forecast prediction for mainland China. And I know that when cold fronts arrive from the north or western north, I have better put a refinement region for the mountains like this shape. Because if I use the coarse resolution, very often the height of the mountains cannot be represented. Usually, it will average out to a lower height. And if in the simulation, the reality have higher hills, but in the model, it is represented by lower averaged terrain data, then the model does not know there is some dragging or blocking effect due to the mountains. And when the cold fronts approach, usually there is a problem that in the simulation, the cold front will arrive too early to the downwind areas. So for practical use, like using a numerical weather prediction model to drive the air quality model, which is called CMAP, to simulate PM 2.5 concentration changes and distribution in the in this area, then we better find some way to make the NWP model to provide a good wind field to drive the CMAP air quality model. So we want some model feature to fix the cold front arrival to early problem. So I want to add resolution refinement to the mountains so that the mountain heights are better represented in the model. However, the alignment, the shape of this area is kind of from southern west to the northern east direction. And if I need to use WRF to add a refinement for the over this slant region, then the area of the high resolution region depicted as this black rectangle would be large. And then I will need to spend quite a high computational cost for high resolution simulation over the whole rectangular area, which actually I may not be able to spend, or I want to lower the cost. So the solution is to use CPAS resolution, a variable resolution unstructured mesh. And I will show it in the next slide. We have a tool that can construct refinement regions of the unstructured mesh in quite arbitrary way, like the example this one. Now I specify the tool to boost the resolution only for the region I specified, like this one. And below it, actually there is cliffs and mountains over Sichuan. So in this example, there is another refinement area, and then so on and so forth. So modifying this generated mesh, you can see that the transition of resolution is actually smooth here. So the benefit of having no abrupt change of resolution is retained in the CPAS model, and yet the shape of the refinement region can be arbitrary. So these are the good features we want. On the contrary, actually, I haven't mentioned another restriction of WRF domain nesting. And in the best practice guide in WRF documentations, it also mentioned that when you have a nested domain, you better have the lateral boundary far away from each other. That means usually the best practice is to use, it is a classical example, is to use a square area, and then you divide the large square into 9 3 times 3 smaller squares. But in this example, I use rectangles according to what I actually want, because I put a focus to the area in the mainland China that have a higher population. So the higher population area is something like a rectangle here. So as I put it this way, actually, I'm not very conformant to the best practice that this edge is too close to this edge. So as I said, the lateral boundary is actually something bad, and some area will come out here. So if your region of interest is too close to the lateral boundary, some erroneous waves or something will actually propagate into your area of interest. So it will lower the accuracy of the simulations. So you can see that with these constraints, if I need to conform to the best practice. I need to use an even larger area of the outer domain, but that will make my computational cost to be even higher. So the benefit of using unstructured mesh is also revealed here. You can have arbitrary shape of refinement regions nesting each other. In this figure, the region with even higher resolution cannot be shown because they all become a patch of blue color. Actually, the resolution of some refinement region or Hong Kong here is even higher. So the unstructured mesh doesn't have the constraints that domain-less thing bring to WRF users. And these are the benefits